Thank you everyone for tuning in to this week's webinar from the Taiwan Space Union. And today we've invited Dr. Pierre Drossart from CNRS, the French National Center for Scientific Research, and the Paris Observatory. Yes,
okay.
and you may begin when ready.
So thank you, Lauren and Wing, for the invitation. I am very glad to be with you, even remotely, as I was during a visit I made in Taipei 3 years ago, and it is a pleasure for me to be with you today. My purpose here is to talk about nanosatellites, and my experience in the field is manifold. I was first head of a department of astrophysique, l'ESIA, Laboratoire d'études spatiales et d'instrumentation en astrophysique in France, which is a laboratory employed in traditional space instrumentation since something like 50 years. And there is therefore a lot of experience building instruments for space. But I have engaged l'ESIA in what is called new space activities with a small nanosat called PICSAT. I will talk more about it. Had also the opportunity to coordinate laboratory activities, several labs in France, mostly in Paris area, in what was called the Laboratoire ESEP, Space Exploration of Planetary Environment. And this was with a branch of activities in the nanosatellites and cubesats. And at this occasion, we were with ESEP at the initiative to create a space campus. We call space campus, and I will also come back on that, a domain of activities to integrate, test small satellites like CubeSat. And finally, I was in charge of a coordination for prospective work at the national agencies for CNRS and the Institut National des Sciences de l'Univers in particular last year. Therefore, I had a global view of what activities are developing in France, and I will exchange with you about that. Of course, the warning is that this is only my own interpretation. I have no of course, possibility to engage any French institution in my talk, and it is only my experience that I share with you with public information of the French research program. First, what is a nanoset? Just a warning, I will call nanoset or cubesat. There is a difference. CubeSat is a kind of nanosat with a specific model and dimensions, but I will use both terms with as synonyms in this course. First, a nanosat is not simply a miniaturized satellite. It is more than that because it involves also what I call an ecosystem to develop end-to-end projects with small teams, a philosophy of development with which is called integrated and iterative, what is called concurrent engineering. That is sometimes not the way big experiments in space are managed usually. Normally, we hope to have short development times. Sometimes it's not so easy, but that is the idea, to have a reactivity, to have small system, just a few science objectives, a small teams with reactivity. And it is also to try to escape to the dilemma of big agencies when you have, of course, the security of the satellite is, of course, predominant. And sometimes new ideas for techniques or for science are not supported because of the risk. So the nanosat allows some different approach in terms of return compared to risk activities. We will come back to that. And there are many constraints and boundary conditions. So first of all, I will talk here about science cubesats or nanosats, science objectives. I'm not talking about commercial developments, which are now in huge development, as you probably know. I exclude also direct application domains, even for technology. I will talk about technology devoted to future science objectives. That's okay. And our science labs are involved in that, but not for technological development per se, and of course, excluding any defense domain activities, of course. The implication of research laboratories has to focus, by definition of our task, on science, and therefore more on science payload than to reinvent satellite subsystems. We say often it is not our duty to reinvent the wheels, reaction wheels for nanosatellites. We are focusing on science. And there is a large involvement in students, internships or PhD, but it is not purely a pedagogic activity. It has to have science objectives. And to do that, the question is which science objectives are accessible? And that is not an easy question. It was very debated, especially in France. We had a lot of resistance from the space sector because they find that the systems are too small to get really science to a quality high enough to be supported. The question of quality insurance, if you want and if you accept higher risk, and if you want to be cheap, there is a definition of the acceptability of the risk to cost ratio, which is, of course, a common question for space activities. But here, probably the cursor is different for nanosat compared to big systems, but still, there have been decennies of work to improve quality insurance for space system, and we don't want to lose this level of quality just to have new system and to start from the ground again with quality. And therefore, that's a question to discuss during a project. The short development need a new strategy for the mission phases. Usually, we don't use usual A, B, C, D, E phases of space agencies, but we can accept some what is called agile procedure, some phases with some reactivity. So we can develop an example if we have a new technology which appears during the development in what is called phase C, the definition of an instrument. It is still possible to reiterate the phase to accept a new instrument, which is usually very difficult in a usual big mission. And small system implies high interaction between payload and satellite subsystems, which is something new for our teams working. I worked in several instruments, especially for Venus Express, where I was PI of an instrument. And you don't care about, well, you care, but you just use what the agency gives you in terms of pointing stability of all the subsystem. On a nanosat, you have to be implied not in the construction, but in the definition at a high level. And there can be also interaction between the software of the payload and the software of the subsystem. So there is more penetration, and the distinction between payload and subsystems is less strong as for big satellites. And for the research activity, we don't want to develop the platform in our lab. It is not our task. And we can have to choose between different kind of platforms. It will be probably a danger to have only a uniform system, and that is one thing. We want to have some flexibility in the choice of the platform. Finally, and not least, there are legal obligations. When you want to launch something in space, there are international regulations, and they apply to everybody, and every citizen in the world has to apply to this regulation, except maybe Elon Musk, but that is another story. And this regulation is translated in the French jurisdiction And this is something usually when you use a small instrument for a space mission. Kness in France or other national agencies are in charge of these legal obligations. If you have a responsibility in a university team or a small research team, you have to discuss, of course, about these obligations with your agencies, and this is something not to forget. So the main actors in France are, of course, starting from the project and a small team with support of laboratories in human resources and technology. There are, for France, the national agency, Kness, Centre National d'Études Spatiales, with the experience of space activities. There are what is called space campus, university space campus or establishment space campus, which I will come back on that, are coordination of the laboratories involved in this new space project. And finally, there is also industrial partners, small or big, depending on the activities, with a lot of interactions between them. Coming now to the new space sector. I call it new space. It is not only nanosats, it can be also small instruments and platforms. But the idea is to have a sector where you have a rapidity in development. In principle, it must be cheap. That still is to be confirmed, because if you have a big objectives, sometimes it can also grow and be of the order of magnitude of a small instrument for space. Cheap may mean, at least for France, in the order of €1 million or $1.5 million US dollars. That is only an order of magnitude, but at least it is 5 to 10 times cheaper than a usual instrument for space mission. We have new institutional actors in France, which are universities were not so much involved. It's a difference with the United States. The research was made by CNRS with some budget coming from Kness, but universities were not so much involved in space activities, and it is not the case for the new space sector. And therefore, there are new institutional actors that they have to be, of course, educated, and we have to discuss with them to explain what our objectives and what the constraints are. There is a large involvement of students, as I said, internship and PhD. And the limitation, you have to make a small mission with very limited objectives, which means a limited number of collaborating laboratories. And that is a big difference with space instruments and big missions like Cassini or Rosetta, etc. Just before going to some concrete explanation, so the recent development in France were piloted by Kness and CNRS. There was a big exercise, research exercise of prospective to make reports, and the result of that is a roadmap for nanosat development, which is being written this year with probably new possibilities to be involved in that. The international situation, you probably know and better than I do. There are many new projects in the world, some supported by universities, some being just piggybacks for larger missions. That is now the rules for NASA missions to get nanosat associated with some of the missions, and also for European Space Agency today. And there is, of course, a growing sector. I will not talk about it for industrial development, but this sector, of course, has consequences for the availability of subsystems and components for nanosat also to be used for science. In France, there are only a few nanosats in flight. There are 4, as far as I know, at least in the sector of science, of course. I have listed them here. I see that you will have a discussion by Mathieu Barthélemy next month on this amical sat from Grenoble, and I will not talk today about it, of course. And the new thing is we may have now a new sector in Kness working with 2 branches of nanosat for student programs, which exist already with Kness, but also for research programs, and that is to be defined yet. And it is new also, it has only 1 year old of activities, a network of space campuses to get some mutualization of the knowledge and information sharing and collaborations. And we have now several platforms directly available for European activities. Some subsystem developments. There are now more and more subsystems we can buy on the shelf, or almost on the shelf. Like, of course, the launch is to be provided by several possibilities, and that is today not so much the bottleneck. There are the structural model, like the test pod you know well in Taiwan. Attitude control systems are now better and better, and micropropulsion is also developing and will probably be available soon for nanosets. For ground segment, that is something not especially new, and that's so much the main problem today with all the communication facilities, either for big system in X-band from the agencies or groups of research, or for, if we limit to UHF, that is accessible to the university. So the challenge, and there are first the technical support. The idea is what to do if I have a new idea in my small team and I want to develop a nanosat. You have to find a technical support, and this can be done through dedicated space campus. You need a strong administrative support. It is important to note that you will have to make contracts, launch contracts. You have to deal with French regulations and so on. So this is not a minor point. Budget, of course, as for every project. But the big, maybe the highest challenge and the most interesting for us scientists is what is the science objectives which are accessible and new, of course. We don't want to repeat what is done elsewhere. And 10 years ago, it was probably not a positive answer, especially in France. Today, the mind of people is changing, and there are new ideas emerging, and I think there is today a positive answer, even if we don't know the place it will take tomorrow in the research activities. For example, this is a list of projects which have been presented for our prospective effort last year in France. So there, it was in the Sciences de l'Univers, in universe and Earth science, but that is probably the main activities today for nanosats. So there is several projects for atmospheric, ocean and surface science, ocean dynamics on continental surfaces for the hydrology, from altimetry, etc. I will not detail every project, just to show you the diversity. And there are also intern Earth projects like magnetic measurements, and there are 2 projects of nanosatellites in Paris on magnetic field observations. In astronomy, there are some interesting cubesat on the gamma ray observations for the chronometry of pulsar, which could be a very interesting approach in exobiology to study the, of course, in space, how the some molecules are degraded in space environment. For planetary exploration and solar system with additional payloads to space mission, because here you will not pay for a launch to, of course, to interplanetary trajectories, but you can use another mission for that. And in solar heliosphere and magnetosphere, there are a lot of proposals. These are domains in the science of cosmology, astronomy, and earth science. In the future, we have to think about possibility to extend to human science. There are certainly some domains which can be interested with such activities, like in sociology, when you look the evolution of habitats in on the world. Even for archaeology from space, there are some ideas for radars and so on. So maybe tomorrow will be also possibilities for doing science with satellites, even for these domains. I will just here describe two examples, one of a nanosat, and I will choose a PIXSat, which I know very well because I was in the lab having piloted the nanosat, which is developed by Sylvestre Lacour, a scientist in Lesia. And I will talk about one of the space campus in France I have worked with in Meudon. So PIXSat was starting from a good science case, which was concerning the Beta Pictoris planetary system, where Beta Pictoris b was predicted to possibly have a transit with a central star in 2018. Finally, to go to the end, the prediction was wrong, but it was at least a possibility to study, and the nanosat was built with these objectives, with secondary objectives to be sure it has a science return in case the transit is not taking place. So that was the science start. And from that, we know how to study planetary transit and occultation by planets. One of the mission and one of the first mission was a French Corot mission. And you see the difficulty, because to study such transit by planets, you need, and the stellarity is a big problem, and you need a big buffer. And you, of course, cannot translate that to a nanosat. Corot was about 1 meter and 1.5 meter large, and that is, of course, not the size you need for a nanosat. So that is the first problem. A second problem is the temperature control. You need a large and very high stability if you want to make transit photometry. And temperature control is, of course, a problem. In low orbit, you will have a large temperature variations you need to deal with. A third point is, of course, the pointing accuracy. If you want a good stability, you need a good pointing stability. Otherwise, the fluctuations are due to pointing errors and not to the variability of the object. So that is are the three main points. And to do that on a nanosat, they had to create a new solution. Instead of baffling, they used the idea to use single mode fibers. And in a fiber, the light is penetrating in a fiber only with a very small angle. Therefore, the baffling is much simpler for this kind of optical systems. There are other difficulties, and the main difficulty is that you have to have a very accurate positioning of the fiber to be fed by the astronomical object. The second solution was to regulate the temperature with a dedicated Peltier regulator, and for the pointing to have the usual cubesat pointing by industrial subsystem, and to have a second stage with fine pointing. And a creative design was built from that. As usual, you take from the requirements, observing the star beta pictories with these characteristics, and defining the observability and all the requirements for the subsystem. That is the usual way, starting from science specifications to technical requirements and building the system from that. To develop the timing, in summer 2015, there was a first bench to demonstrate the concept. In particular, the volume of the system was shown to be fitting in 10 centimeter, 1 liter volume. And they were beginning to develop the algorithm for tracking, which was a large part of the development also. In winter, they made the first vibration tests in usual vibration pods for space experiments, thermal cycle, and some radiation tests also. Early 2016, there was the first complete version of PIXAT with optics system, pointing system with piezoelectrics table and electronics. In summer 2016, the validation started with testing, and I will come back on the question of how to test and have the facilities to test nanosets. And in winter, the validation of the pointing, the second stage of pointing, was obtained in the lab, at least in one dimension, and that was a very good success, and it was mandatory to have the flight of PIXAT. In summer, the onboard computer was developed. This was made through development in Lesia, and thanks to the capacity of the lab to support high quality flight computers, software development in a space environment. We bought a ground segment system with simply UHF antenna, and in winter it was ready to fly and tested in December 2017. The launch was made on an Indian launcher in January. And this is a system, the orbiter of the orbit was a low Earth orbit in polar orbit with 500 kilometer altitude. And a system of telecommunication with a UHF ground station. Thanks to the ground station, it was possible to observe PIXAT twice a day because of the orbit period from our Meudon site. And there was really a big project, which was to use the radio amateur community to help to retrieve the data from PIXAT. And it was really a big venture because we had hundreds of volunteers from this community, which were able to get the data package and to send it to Lesia, which was, of course, very interesting because we had much more coverage and temporal coverage for data reception, and emission was only from Meudon, but reception was made all around the world, including Taiwan, in fact. And the end of mission, unfortunately, was too soon in March, probably because of high geomagnetic activities and radiation belts in the South Atlantic zone. That is the best interpretation we have today. So it was a failure in terms of science return, but interesting in terms of data. We had a lot of data, for example, for our subsystem, for the temperature control, this is the excursion in temperature for the payload from more than 10 degrees in excursion. And this is the stability on the detector level, which is less than 0.1 degrees. So that was very good. And we have an heritage, a good expertise, and a team also. We demonstrated the possibility to build a team in a short time. And the post-operation was made very professionally with a full international team review with Kness and ISA participants to get all the return of experience, to know what was what failures was made, what is not to repeat in the future. And there are many possibilities to use a PICSAT system for future mission. For example, the Ariel is a mission to study also transit of exoplanets. We'll need to prepare a catalog of planets in advance. And for that, having a nanoset system to support the preparation will be interesting. And it is studied by the project Ariel to support some of this possibility. And there are future possibility also to use fiber optics to make interferometry with 2 or more nanosats, which will be, it is a medium future, not for the next few years, but it could be very interesting to get this kind of system, even in the field of gravitational wave detection, for example. You always think to big systems like LISA project from ESA and NASA, but it is not totally impossible to get much simpler systems with lower capabilities, but with possibilities to have some work in this field. Now I will pass to the definition of space campuses. There are today about 12 or even more space campus in Paris area, 5 of them, and in all France. And you will see by Mathieu Barthélémy in Grenoble, probably the presentation of the space campus of Grenoble next month. And what is the role and what is how is it useful to have a space campus? I will present here what we have in Meudon, which is called the census. And I was at the initiative to create this project. Now I have passed to Coralie Neiner in Lesia, my direction of the project. So there are 3 pillars: the science, always, that is our main objective always, technology developments, and Boris Segre, that you well know here in Taiwan, is in charge of that. And for education, Benoît Mosser, which was also a visitor in Taiwan a few years ago, is in charge of education parts and internships and so on. So there are a scientific committee, development of an ecosystem with all the facilities, and there is a possibility to have students and attract students for different origins to work in this project. In terms of what is called the model-based system engineering method, it is something well adapted to projects like NanoSat. You define, it is called the concept of maturity level. It is like the technical readiness level, but with more flexibility than is the TRL, which is sometimes too rigidly applied to necessary for a big system, but not so much for smaller systems. And the collaboration and to work together with different specialties is the DNA of NanoSat projects, I would say. There are tools, engineering tools, which are professional tools we use for a census tool developed by Kness, which is called DOCS, which allows concurrent facilities for all the engineering data needed to specify a space mission, with the pointing and the orbit parameters, the thermal and thermomechanical issue, the data link issues, etc. All that in one software shared by different engineers. And we do that in a room, what is called a Promise Plateau, which is a room where you work together, even remotely. I think there are several sessions having been made with Tainan by Boris Segre and Odysseus startup. And at the end of a session, usually 1 or 2 weeks, you finish with a definition of emission, preliminary design of a emission, which is now of a high quality. And even if you go after two big space agencies, having made this work in advance gives you an advantage compared to a system you have only studied on the shelf on your own lab. When you go to the integration, you need, of course, a clean room. That is also a system we have in Meudon. It has been developed, and we have a clean room dedicated to nanosatellite. It's called the Vega room, and it is not the highest quality clean room, but it is enough to develop components in a good property environment and with the usual system. One word about concept and the components on the shelves. On the shelves is sometimes you think you buy your system and you can integrate it. It is not the case for nanoset. First of all, usually you buy subsystems which will need space qualification. And that is where space campus are important, because we have the expertise working with big space science instruments. We know how to do it to make, for example, the thermal environment thermal testing, which is mandatory for going into space. There are some radiation tests which are usually not available for components on the shelves. All that you can have a cheap mission with not already qualified components if you are able to qualify themselves from your space campus. So that is an important part. And then there is a ground segment. And if you want to go beyond the UHF bands, you need, of course, a bigger antenna, which is probably not or only rarely on the capabilities of universities, but can be shared with other projects, space agencies, and so on. So today, the communication, and you can work in S or X-band without problems with nanosats, if you have the connections with, of course, the ecosystem of space science, not limited to nanosats, but also to other projects. So for future science and approach to the end, and I would like first to describe some possibilities of future development. There is a strong need to help major mission, for example, in support of ESA or NASA mission. And the reason is when you select a big mission, it is the same for NASA and ESA, and I suppose for other countries. The main objective of the agency, if you spend 50 or $100 million or even much more, you need, of course, a return on investment and to minimize the risk. This is sometimes at the expense of the creativity. If you have a new system, and it is in the concept of TRL. TRL 8 is a system which has already been in flight. And if you fly an experiment, well, if you want to reuse it is not a new system. It is not, and if you have a new instrument, that is a long, long way before it is qualified. And it means you can spend 10 years before concept and the fly. With nanosat, you can do it easier, make it easier and more rapidly. And also, you can tell to the agency, this is a nanosat. It is not part of the big science mission. Therefore, it is higher risk, but it will not jeopardize the full mission. If it fails, it is not the full mission objectives which are lost. It is only the nanosat. And it works well. You have NASA selecting high-risk mission. One example may be the helicopter. It is not exactly a nanosat, but the helicopter on Mars. or other subsystems, they are accepted on a big mission because they are not in the main stream of the science objectives of the mission. Therefore, there is a niche science there for small additional payloads for system. For interplanetary trajectories, which are of interest, of course, for our planetary scientists, as I am myself, the challenge is also for CubeSat. We have a project between Taiwan and France about that, Birdie, and we hope it will help define some system like that. And to finish, I will show you a project for the future. Probably it will need 10 years or more before being designed, but that has been presented in the ideas to European Space Agency last year by Baptiste Secconi in radio science. It is called the Noir project, and it is a swarm of nanosatellites with 10 or even more nodes to look at low frequency in radio astronomy and to have some science payload with receivers from 1 kilohertz to 100 megahertz. What is the science interest? It can be huge for to have such a network of nanosat around the Earth, or even if we dream a little more around the Moon, for example. You have a low cost for individual satellites. The cost is high because of the high network. And therefore, you can have a relatively fast development track. Then there are new challenges. And the highest challenge is you don't want to have a control room on Earth to have an operation of 50 nanosatellites at the same time. That will be very costly, very expensive, and that is not the way to do it. If you want them to have some autonomy, you need to invest in artificial intelligence system, which still don't exist, but which probably will exist sooner or later to operate autonomously such kind of network of satellites. If we dream to that, maybe in 10 years, you will be able to get multiple science topics in cosmology, interstellar matter, high energy, astrophysics, and solar system too. So that is really something to look at. It's maybe a dream today, but we know that the reality of tomorrow is the dream of today, and therefore that's certainly something to look at. And I will conclude that to say that today, definitely, nanosats have already found a place in the space sector, a small place, but which can continue and maybe grow in the next decade or so. And it is probably the beginning of a new era, and we will have support activities for larger missions, autonomous nanosat for dedicated objectives, with replacement of some activities to have continuous operations on some measurements made by nanosats. And space scientists of today cannot ignore this domain if we want really to develop our own idea on a new system. And thank you for your attention. Finish here.
Okay, thank you very much, Pierre. It's very interesting, the work that you're sharing. And of course, one thing that we find particularly interesting is the presence of so many space campuses in France. For example, at our university, we hope to establish something similar, but we're very curious about how are these space campuses in France funded and supported? Is it by the university, industry partnerships, or does Kness support them?
Good question. First of all, I will show you the list I showed to discuss. First of all, some are just it is some are very small, some are really operational. I will say one operational, and it is the first one, was in Montpellier with the first nanosat by Laurent Dussault several years ago. It was the first flight of a nanosat, and now it has a good facility, and it is financed with partnership with L'Air Liquide, a society in France, which is supporting clean room developments for their own use, but with sharing with the Space Campus. Census is already big enough, thanks to the LESIA, because we share some facilities for space instrument together with the space development for nanosat. Some others are smaller, cubesat, Paris Diderot, and those are essentially clean rooms and laboratory rooms with some management behind, not more. Grenoble is now also a good shape, but Mathieu will probably describe it to you next month. So the development, sometimes it is only a few persons and a clean rooms, and some are relatively medium center. Concerning the budget, yes, universities are, they want the visibility. That is due to the system in France of universities compared to research institutes. University wants some visibility at the international especially. And space sector is, of course, a good visibility. If you have only a small subsystem in a big satellite, in fact, your visibility is not so large. And university prefer to have a small, limited system, but to have from their own property. And that is where new universities are funding. And this is true for Paris Sciences et Lettres, for Census. This is true for cubesat at Sorbonne University, and so on. And that is at least a level of action. Of course, Kness is a large partner for information sharing, and not so much for budget today, but it can change. The budget was up to now mostly for student partnerships, but it is changing. They are now also interested in budgeting for science nanosat. So it is moving very fast, but the budget is, of course, as always, the weak point as for any project. Then you have the usual agencies for European or national is probably too small, but European or even European Space Agency or European Union for France.
Okay, thank you very much, Pierre. It's certainly very exciting, and it's something I think we have a lot to learn from. Are there any questions from the audience? You can either raise your hand or type your question in the chat. In the meantime, I'm also very curious. So for these small satellite projects that you've been involved in, are they managed in a way that's different from a traditional large satellite project? For example, does Kness still require all the documentation, all the reviews that they would for a large satellite, or is it more of a simplified version?
Yeah, good question too. Yes, Kness has always an eye when you talk to space activities, of course. First of all, to verify that you are using the good rules in terms of the legislation. And you cannot do anything in space, especially when you are dealing with the space debris problems, as you well know. Therefore, you have, for example, to prove that your battery will not explode in space and so on. This needs a verification, and this is done by Kness, which is a regulatory agencies. It is not piloted by Kness itself, except for a few projects which were made by Kness itself. But otherwise, the responsibility is for the CNRS, for example. I had myself in fact, troubles, because as I head of department supporting PIXAT, I had to convince the director of the CNRS agency that yes, he could sign the contracts to launch a satellite, which is not his usual job. So it was the first time he had to do that, and of course he was afraid of possible responsibility. So that was some discussions we had to have because the budget came through the CNRS, and it was not a Kness project. It was unusual. Today, that is also the question that where Kness is naturally the agency to be involved, even if it is not the main budget provider.
Okay, I see. So they sort of serve as a regulatory and advisory body. Is that correct?
Yes, and we'll also we had to have a post-mortem review, and that was done also with Kness participation. To just ask for any mission, even if they are not controlling the mission by themselves, as for usual space instruments, they are still involved. And with our agreement, of course, we work completely with this partnership.
I see. In the case of PigSat, what was the size of the team that you used to build and operate the spacecraft? And what was the proportion between students and, say, professional engineers or faculty?
In fact, so I think Sylvestre Lacour made the total count of people. But from memory, I would say at the main part, there were less than 10 persons. And with some help, of course, for example, at one time, they were designing the mechanics. And this was with help of Lesia. We have mechanical engineer. They were at top level for space instruments. And there was a few, maybe 1 month, not more, of these qualified persons. Same for the software. It was made by a space qualified engineer. And it took several months of work this time. But the project manager, at the beginning at least, was a PhD student, very high level. It was very interesting for him, of course. And it learned everything by himself to deal with a project. And it was a chance for Sylvestre. Sylvestre was not a space scientist before, therefore he had also himself to learn a lot about that. So he's a PhD student and an engineer which was recruited for the project. So those were the 3 main persons. Then a lot of help from Lesia and for the administration in particular. So the environment of Lesia was mandatory to have the success, at least the first success of until launch of PigSat. And that is a difficulty sometimes if you have 2 large students projects, especially if the project manager is a student with no experience. That is not so easy to go to the end of the project. And that is sometimes a problem for student nanosets.
Definitely. It must have been a very exciting and I'm sure intense experience for the students involved. So I'm sure many lessons were learned from the development and operation of PigSat. But of course, one issue with running university space programs is your students tend to graduate every 2 to 5 years. So how do you ensure that the lessons learned from the mission are carried on and passed down to new students in the program?
That is also a difficulty. You have to pass the expertise from one team of students to the next. And this means you have to deal, I have not mentioned it, but that's also an important part of any project. It is the documentation. Space documentation is a part of, you need usually a qualified engineer in documentation to get proper documentation. And it is especially important when you have a rotation of the teams from one student to the next one. And that is usually where newcomers in university are sometimes at a difficult time when they don't have all the expertise of the environment of space lab behind. So the best success today in nanosats are made by space laboratories, which accept to share their expertise with some university labs or with some teams which are not in their mainstream activities, but they find an interest to help in that.
Okay, a challenge we all face. Are there any questions from the audience for Pierre? Okay, I guess the presentation was very clear. So
thank you.
If there are no additional questions, then thank you very much, Pierre, for taking the time to share your very interesting experiences. We wish you the best of luck with Noir.
Thank you, and I hope we will have on other occasion to work together with your teams, and I'm sure I will be interested to participate. Even if myself I have now passed the button to coordinator for the census team, but I am still close to them and I keep an eye on the new developments in these activities.
Okay, thank you very much, and look forward to when the whole world opens up again. Look forward to seeing you in person, and you're always very welcome to come visit.
Yes, I have a very good memory of my visit to Taiwan 3 years ago.
Okay.
Thank you.
Thank you very much, Pierre, and thank you very much, everyone, for participating. And we hope you found the webinar informative and enjoyable. So until next time, thank you.
Until next time.
Okay, bye-bye.